Okay, so this video is for the last page of the Chapter 1, or Chapter 7, Notes 1 handout. And this is about interest and compound interest. And the way that interest typically works is you invest some money in the bank and you earn however much you earn on it. And then that sits in the account too. So you have more in the account now, and that earns interest. So you keep compounding on top of whatever you already had, and so the money that you earn starts to grow faster and faster. And the way that it gets phrased sort of varies. You can say that you have an annual interest rate, and but it depends on how often you do something called compounded. So if you say, well, you have a 4% interest rate each year, but you compound once a month, then really what you do is you take the 4 and divide it by 12, and that's your rate for the month. So let's look at, this is the formula for it right here, right there. So there are a lot of variables. A is the amount of your investment. P is the principal, which means how much did you originally invest. R is going to be the thing called the annual interest rate, but you have to turn it into a decimal. And then you're told how often you compound. Maybe you compound once a month, or you compound once a week. So if it was once a month, then you'd make N 12, because it's 12 months a year. If it was once a week, you make N 52, right? And then T, and that's the same N, and then T right there is going to be the number of years. So that your investment is going on. So let's say here you spent $2,000, or you put in $2,000 into the bank, and you get 4% annual interest. You're going to find the balance after 3 years. Well, we'll worry about that in a second. If the interest is compounded quarterly, once every 3 months, 4 times a year. Okay, so our formula would then be, if it's compounded quarterly, that means N is 4. We know that our rate is 4%, so that's 0.04. We're going to find the balance after 3 years, so eventually we'll set T equal to 3. And then our initial investment was $2,000. So when we write out our formula, with just the T still there, we've got the initial amount, 2,000, times 1 plus the rate, the annual rate, compounded 4 times a year. And then we're going to raise that to the 4t. Really, this number up here is how many times did we compound. So if I'm compounding it for 3 years, 4 times a year, then that whole number is going to be 12. So, and that's what we're going to do. So let's look at A of 3. It's going to be 2,000 times 1 plus 0.04 over 4 to the 4 times 3. And then we'll just plug this into a calculator here. Turn it on. Let's see, 2,000 times 1 plus 0.04 divided by 4. Whoop, divided by 4. Division's not working. Divided by 4 to the 4 times 3. Ugh. Come on, calculator. Times 3. Enter. $2,253.65. Okay, so that's if you compound once every 4 months, or 3 months, 4 times a year. Well, let's see what happens if we do it once a month instead. Now, typically, if you keep the same annual interest rate, the more frequently you compound, the better your investment pays off. So if you compound it monthly, that should be better than quarterly. If you compound daily, that should be better than monthly. It's marginal changes. It doesn't change a ton, but over the long scheme of things, if you were doing this for 100 years, it would pay off a little bit better. So let's look at what happens if we compound monthly. So monthly is going to be, I'll use a different color here. Monthly is going to be N equals 12. So if we write the general formula with t first, we've got 2,000 times 1 plus the annual rate. But now instead of cutting it into 4 chunks, we're going to cut it into 12 chunks. And then when I figure out my power, I'm not doing it to the 4t, I'm doing it to the 12t now. Okay. Let me rewrite the formula over here so you have it. The general formula is going to be a of t equals the principal 1 plus the rate divided by the number of times that you actually compound to the number of times per year times the number of years. It's a lot in that formula. Okay, so we want a of 3 because we care after about 3 years. So 2,000, 1 plus 0.04 over 12 to the 12 times 3. And let's type that in. Actually, I'll just call up the previous one and then edit it. So 4 is now 12. And then I've got a 12 up here instead. 12 times 3. And let's see what we get. Okay, so it's 2254.54. So it's a little bit more, right? Well, let's see what happens if we do daily compounding. So it's not really 4% divided by 12 anymore. Now it's going to be 4% divided by 365. So our formula, 2,000 times 1 plus 0.04 over 365 raised to the 365t. Okay, and we want a of 3. What's our investment after 3 years? 2,000 times 1.04 over 365 to the 365 times 3. And let's see what that comes out to be. So, come back over here. 12 is now 365. And then we're going to raise it to the 365 times 3. Oh, I must have messed something up. What did I type in up here? Oh, I still have that 12 to the 3rd up above. Okay, so I gotta get rid of that. Yeah, that seemed way too big. Let's see. There we go. That seems more reasonable. $2,254. And that would be 98 cents if we round to the nearest cent. So you can see the more frequently you compound, if you only do it 4 times a year, you have this amount. If you do it monthly, you get a little bit more. If you do it daily, you get a little bit more. So it turns out you could compound even more frequently. If you wanted to, you could compound every hour, right? If you wanted to do every hour, you'd have to take 365 multiplied by 24, and that would be your new n, right? So that's what's right there. You could do it every minute. So then you take the number of hours and multiply it by 60. You could do it every second or every millisecond. You can get really, really tiny. So the idea is that at some point you could compound every single instant all year long. And that's called continuously compounding, right? You can't even count how many times you compound. The idea is that it approaches infinity. So that's this idea. You make n get bigger and bigger and bigger. But there's no way of plugging that into a calculator. You can't just plug in infinity. Well, it turns out that mathematicians have figured out a different way of doing this. And the formula up here, this formula, if n actually becomes a massively large number, that formula turns into this one instead. So if you compound continuously, then you end up turning that other formula into something that looks like this. I call it the Pert Formula. Really, it's the continuously compounded interest formula. And E is a number. It's kind of like pi. You know how pi is 3.14, blah, 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 and it's a decimal that never ends. E is like that too. E is a number that's about 2.71. And there's a button for it on your calculator. And it is right here. That little blue thing is E. So if I hit second division, you get the E button. And it's 2.718. Blah, blah, blah. That's not a repeating decimal, by the way. It looks like it might have a pattern. It doesn't. It's like pi, where there's no pattern to it. And it turns out e is an incredibly important number in math, especially when you get to calculus and economics and statistics, things like that. It ends up being pretty important. So let's say that you decided your investment gets continuously compounded. So it's every single instant forever. So then let's fill out our formula for continuous compound interest. The principal, what was the amount that we invested again? I don't remember. $2,000. And then it's just the number E, and the rate was 4%, I think. Let me check. Yeah, 4%. And we're doing it for 3 years. So if we do that, we're going to get, let's type that in, 2,000 times e to the 0.04 times 3. 2254.99, which is a few cents more than the other one. Right there. It's 1 cent more. It's not even a few cents more, but it is more. So the more often you compound, the better off your investment ends up being. Okay. I hope that helps okay. Let me throw one sample problem at you just so you see it. And this isn't on the page, but let's say you wanted, so the question is, when will your investment be worth, let's say, $3,000? Okay. And we're going to assume that it's continuously compounded. All right. So that means we want A of t to be $3,000. So we set this up. 3,000 equals 2,000 times e to the 0.04 t. Right? That's our general formula. Whoops. This is really A of 3. Normally it's just a t there. So the goal now is to figure out what t is. So if we do this, let's divide the 2,000. So we get 3,000 divided by 2,000 equals e to the r t. 3,000 divided by 2,000 is 1.5, 3 over 2. Okay, and now we got to figure out what this thing is. So remember that change formula from log to exponential form. So let me write that out for you. Log base b of a equals c means the same exact thing as b to the c equals a. Remember, these two things are equivalent. If you know one, you know the other. So let me write what we have right underneath the b to the c equals a, because that's the form that we have. We have e to the 0.04 t equals 1.5. And we're looking for the exponents, so that's why logs come in handy. So if I switch that, I've got log base b, which is base e, which is a number, and then a is 1.5 equals 0.04 t. Now the nice thing here, let me get rid of that cloud so we can see the red better. So this is what we have now. I can solve for this side now because it's a log where e is a number and 1.5 is a number. So if I come back to the calculator, I can go to alpha F2 and come down here to log base. The base is e. The inside here is 1.5. And if I hit enter, 0.05465 equals this part. And then I've got that equaling 0.04 t. So now I need t. I'm going to divide both sides by 0.04. And so that means t is going to be, let's divide it by 0.04. 10.0 137-ish, right? So that's how many years it'll take for the investment to become $3,000 if it's compounded continuously. By the way, there's another way of writing log base e of 1.5. It turns out if the base is e is such an important number that if you have log base e, they have a special term for it. That's actually called the natural logarithm. And so that gets written this way instead. You write ln for logarithm natural, I guess. I don't know. Maybe it was from some other language where n would come after, but it's the natural logarithm of 1.5, and that has a special button, and it's located right here next to the 4 ln of 1.5. And notice it's the same 0.4054, 0.4054. So it's the same thing. It's this right here. Yeah. Okay. Hope that helps. Yeah, then you're all caught up with the lesson.